At the end of the previous section, the textbook was talking about something called rearrangements. And what they're referring to is rearrangements of the terms of infinite sums. Okay, so let's take a look at what happens if we rearrange the terms of the alternating harmonic series. And when we do this, it's going to seem like math is broken. Okay, so the alternating harmonic series. All right, so let's write this out in the term form. So we start with positive 1, then minus 1/2, plus 1/3, minus 1/4, etc. And I want to write out a bunch of terms just to illustrate this clearly. And this goes on to infinity. Okay, so we've shown how to prove that this series is convergent. So since this series is convergent, we know that what that means is that we can say that this is equal to like a number, s. We can't say, like, we can't put this s equals to, a variable is equal to, until we show that the series is convergent. So since it's convergent, that's what it means. That means this series is equal to a number. Okay, so now next what we're going to do is let's multiply both sides of this equation by 2. Okay, so now what I'm going to do is I'm just going to write this out without simplifying anything. So 1 times 2 is 2. 1/2 times 2 is 2 over 2. Okay, so everything good so far, right? This pattern goes on to infinity. So now let's go ahead and let's simplify these terms. So 2 minus 2 over 2 is 1. 2/6 is 1/3. Okay, so we've got 2s is equal to this 2 minus 1 is 1. And now we can think about combining the fractions that have the same denominator. And the way it's simplified, it ends up being that you've got this pattern of even denominators by themselves with just a 1 in the numerator. And this comes from, these are coming from, so we started off where all the numerators were 1s. So we multiply by 2, so now every single numerator is 2. So what happens is you either have a denominator that's odd, and so the fraction doesn't simplify, and the numerator is 2 with an odd denominator, or you have a 2 in the numerator with an even denominator, so you end up with 1 divided by an odd number. Okay, so what happens is we just have these 1s in the numerator with an even denominator by themselves. So let's to put the denominators in increasing order, let's bring the minus 1/2 to the in front of the 2/3. And then we've got this, we multiply 1 over 3 by 2 and got 2/3. And then here, this was the 1 over 6. So we had 2/6, which simplified to 2/3. So we have 2/3 minus 1/3, that's plus 1/3. So now we've got this 1 minus 1/4 by itself. Let's bring that to, again, we're putting the denominators in increasing order. Then so the 5 in the denominator, we've got 2/5 minus 1/5. It's plus 1/5. Okay, then what's next? There's going to be a minus 1/6 by itself. And then you'll have a 2/7 minus a 1/7 that we can't see. Then you'll have a minus 1/8. And that pattern goes off to infinity. But the issue is, look at this. What is this? This is the alternating harmonic series. This is exactly equal to this. But this is 2s, this is s. So what's going on here? What's the problem? Well, when it comes to this issue, only comes up with conditionally convergent series. If it's absolutely convergent, there's no issue here. It's only with conditionally convergent series does this problem happen? And it's the issue. The problem is it's the order matters. The order in which you add matters for these conditionally convergent series. That's what you have to keep in mind. But the problem with that is that seems to violate what we know to be the commutative property of addition. It's called the commutative property of addition. That's kind of confusing. They call it that, and they say subtraction is not commutative because, A minus B is not equal to B minus A, right? So you can't apply the commutative property to subtraction. Oh, so that must be the issue, right? You can't switch the order when you're subtracting because that's not commutative, but that's, we know that you absolutely do this. You can say that A minus B is equal to minus B plus A. So in this context, this is commutative. This series here you would think should be commutative. But the rule is that you don't treat a conditionally convergent series as if it's commutative. And so, but still, that seems to be, we're breaking math. Like, what's the problem? The best explanation that I've heard is that you have to remember with these infinite sums, even the ones that are absolutely convergent for all of these infinite sums, it's a definition that was made. It's a limit, right? So like, it's, we talk about how limits, a limit could be equal to something, but we never think about the limit that's at that actual number, right? The limit doesn't apply at that number. So, but I don't want to say that and act like, these infinite sums are, by definition, and the definition is very intuitive, these infinite sums are equal to actual numbers. Okay, but I'm just saying that since it's a limit, it's like you would have to be applying rearranging infinitely many numbers. You'd have to be applying an infinite number of rearrangements. You'd have to be applying the commutative property like infinite number of times, and it's like, can you really think about doing that? Okay, and so this is really paradoxical. It's a head scratcher. But remember, this is only an issue with conditionally convergent series. And yes, while these infinite series that are convergent are actual sums, and you can absolutely think about the idea of summing an infinite number of terms, it still is, we're still talking about a limit though. And like the context of like the commutative property of addition, you're not thinking about like doing that infinitely, an infinite number of times. And so with that, you could think about that. It's not that implausible that some ambiguity might come up with certain types of infinite series that are like right on the border of convergence and divergence, like the harmonic series, right? It's divergent in one sense, convergent in another sense. Now, something you could also look into, you could do a YouTube or Google search, is the Riemann rearrangement theorem, I think it's called. And what is proven is that any conditionally convergent series, you could do a rearrangement and then with that rearrangement show that the infinite series is equal to anything, any number from negative infinity to positive infinity. So you could show that it's divergent to positive infinity, divergent to negative infinity, or convergent to any real number. Okay. Now, however, though, last thing to note, and this is really important, is that the way we approach conditionally convergent series is that we state that the order matters. And so if you have a conditionally convergent series like this, then it's implied that, the order going from n, n is in order from 1 to infinity. And so the rule is you're assuming that the terms are in the order stated by the sum. And so if the alternating harmonic series is in this order, then this is equal to, you can show that this is equal to natural log of 2. And so that's what the alternating harmonic series is. You would state that it's equal to the natural log of 2, with the implication that you're assuming that the terms are in the correct order. However, you don't have to make this kind of implicit assumption for any other series that's absolutely convergent, because the order of the terms doesn't matter in that case.